A very good morning, students. We are back with our structural geology video lecture series, and today's topic of discussion is the Anderson's theory of faulting. So in this video I will try to explain what is this faulting classification and why it is important to read this classification. Okay, so far what we have seen is classification of faults like normal fault, reverse fault, strike slip fault, like this, right? So all these classification is primarily based on the angle of fault plane along with the relative displacement of fault block. Like if you take a normal fault, you will say the fault plane is inclined and the hanging wall moves down. Whereas in case of reverse fault, you can see the hanging wall is moving up. Whereas in strike slip fault, the fault plane is parallel to the strike as well as the displacement is also parallel to the strike. Do you remember those things? So in this case, in terms of Anderson theory of faulting, Ernest Amazon Anderson in 1905 classifies the geological faults based on the orientation of principal stress related to the earth's surface. So far what we had seen is the classification based on the apparent displacement. In this case, we are just dealing with the fault classification which is primarily based on the orientation of the stress direction, like sigma 1, sigma 2 and sigma 3. As some of you may know what is it, let me explain what it is. Sigma 1 is the maximum stress direction, whereas sigma 3 is the minimum stress direction and sigma 2 is the intermediate stress direction. So the sigma 1, that is the maximum stress direction, indicates this is the direction in which the maximum amount of stress is applied. Whereas sigma 3 indicates this could be a possible displacement direction. The reason is that when a force is applied in one direction, the resultant will be on the other direction, right? So the force applied will be the sigma 1 and the resultant displacement could be parallel to the sigma 3. That is what a generalized theme or generalized thing about this. Let us try to link this three direction in terms of fault classification. Is that okay? Right. So what is a reverse fault according to Anderson theory of faulting? Okay, so let us make it very concise because I just want to make a short video. That's why I'm just making a very short points in this. A reverse fault, which is a compressional regime, right? As you know, the compressional regime, extensional regime, which is in tectonic boundary, right? So the sigma 3 will be vertical. So you can see the image here, which is indicator of reverse faulting. In this case, you can see sigma 3 is vertical. As I said earlier, sigma 1 will be the maximum stress direction and sigma 3 will be the direction that is parallel to the direction of displacement. And in this case, the hanging wall actually moves up. So it is a reverse fault, right? So the sigma 1 is horizontal and sigma 3 is vertical. Okay, and here the fault plane is somewhere near 30-degree inclination. Okay, so this is what Anderson theory of faulting explains here. Along with the displacement direction, there is a angle of the fault. So these two were related or linked in the Anderson theory of faulting. Then what they are mentioning here is a state of horizontal compression is defined for thrust faulting. So here the horizontal stress is maximum, that is sigma 1 is in horizontal. So the resultant here is vertical. Okay. So this is for reverse fault. Let us see what he mentioned as normal fault here is the sigma 1 is vertical. As you know, sigma 1 is the maximum stress direction and sigma 3 will be the direction in which the displacement takes place, right? So here it is horizontal. So in this direction there is a displacement. So this comes under normal fault, where sigma 1 is vertical and other two are horizontal, and this will happen in a tensional or extensional regime. And here the fault plane angle could be in the range of around 60 degree, and this is formed due to the horizontal extension or vertical compression. So both can be possible, that is a horizontal extension can lead to the formation of a normal fault, or a vertical compression can also be leads to the formation of normal fault. In this both the case, the reaction will be, that is the movement will be same. Okay. So the third classification of faulting that we are studying is the strike slip fault. As we had seen the sigma 3 and sigma 1 vertical, so the last probability is sigma 2 is vertical. Here you can see the sigma 2 is vertical. In this case, sigma 1 as well as sigma 3 is horizontal. So the maximum stress direction and the minimum stress direction is horizontal. So the displacement will be along horizontal. That's why it is happening as a strike slip fault, and the fault plane here is 90 degree. And here the displacement is due to the horizontal compression. Okay. So these are the three broad classes fault in Anderson theory of faulting, and these are the setup of sigma 1, sigma 2 and sigma 3 in terms of this fault classification. So let us see what are the limitations in this sort of classification. So the very first thing is it actually misses the low angle fault. So we had mentioned that a strike slip fault will be 90, reverse fault will be 30, and a normal fault is somewhere near 60. But in some cases you can see a normal fault at lower angle, or even a reverse fault less than 30 degree, right? That is a low angle reverse fault, which we used to call it as a thrust fault. So such a kind of faulting cannot be explained in this theory. So that is the very first limitation. The second one is that, as you know, the strike slip fault, dip slip fault, right? There is oblique fault, which is the displacement is not parallel to strike as well as not perpendicular to strike, that is parallel to dip. It is at certain angle. So this sort of oblique faulting cannot be explained in this theory. It is Anderson theory of faulting. So this is the second limitation. The reason for this limitations can be expressed by three reasons. One is this Anderson theory assumes the rock is homogeneous in nature, but in general Earth's rocks are heterogeneous in nature. So that would be the first reason. That is why this sort of other classification of faulting cannot be explained in the Anderson theory of faulting. The second cause could be the ignorance of pore fluid pressure effect. So if there is a pore fluid, like we are dealing with the rocks, right? So there could be pores, especially if you are dealing with a sedimentary rock, there could be a larger amount of voids, that is pores, up to say 30%, which could be filled with groundwater or any other liquid. So this pore liquid could drastically change the orientation of the resultant strain direction and the amount of stress required for the formation of such a kind of strain. So the ignorance of the pore fluid could also lead to cannot explain this sort of fault classification. And the third reason is it does not account for pre-existing weakness. So if there is a rock is present and there is a weaker plane which is present in the rock, if there is a stress act on that particular rock, the deformation could be more along the pre-existing weakness, as it is a earlier formed weaker plane that could reactivate, right? So this could also be possible for not explaining the other classification of faults with the help of Anderson theory of faulting, right? So these are the limitations and exceptions in this classification. And let us see its importance in structural geology. The very first importance is that the stress fault relationship. So whenever we are studying about the fault, it could be having some sort of relation with the regional stress, which in previous case, like when we are studying about the classification of say strike slip, dip slip, oblique or bedding fault, all those classifications, right? We had covered almost 3 into 3, somewhere near 9 classes, right? So all those classifications are primarily of geometric, and sometimes it could be like genetic, but no any classification, or at least not exactly explaining the overall stress regime, like sigma 1, sigma 2, sigma 3 were not explained in those classifications. So in this classification, we are linking the stress along with the fault classification, which is a prime important for a geologist to understand the overall tectonic setting of a particular region, right? So that is the very first important reason. The second is that seismic and tectonic interpretation. Like if you see a deviation from a predicted dip, indicates post-formational tilting, pre-existing weakness or anisotrophic rock behavior, and this could help reconstructing the paleo stress field using fault orientation. So according to Anderson theory of faulting, a normal fault will be like in 60-degree and a reverse fault would be in the range of say 30-degree, right? If you see a reverse fault, which is a very low angle reverse fault, which we used to call it as a thrust fault, that indicates there could be some sort of pre-existing weakness, or there could be some sort of anisotropism in the rock behavior, or such a kind of other setting which is a paleo stress setting that could be understood with the help of the study of Anderson theory of faulting. So let us see some of the applications of Anderson theory of faulting. The very first application is that hydrocarbon exploration. So when you are dealing with the hydrocarbon, we are mainly interested to find the trap rock or the cap rock, right? So a petroleum will form at some other location and it will migrate all along the path that is conduit that is present, and it will be trapped when there is a block in its movement. Like if there is an anticline that could act as a trap for a petroleum. In the same way, predicting fault, seal potential and traps. The Anderson theory of faulting will help us to understand the presence of a particular kind of fault and its orientation. Along with that, you can expect there could be a formation of a trap for the petroleum. So for such a kind of hydrocarbon exploration, this Anderson theory of faulting could be helpful. The second application is that earthquake hazard analysis, that is identifying active fault regime to assess the seismic risk like thrust faulting or subduction zone. So the kind of fault that is related to the kind of tectonic setups could help us to understand the depth of which a earthquake could form. Not only that, or we can also try to expect or say fix some limit for understanding about the magnitude of the earthquake. The third application is the mining as well as geotechnical engineering, as this Anderson theory of faulting will guide us to understand the stability assessment in underground excavation by analyzing the stress induced faulting. So when you see a fault, say in a mining location or anything, according to the fault you can find the orientation of the sigma 1, sigma 2, sigma 3, that is in which direction there is maximum stress. According to that we can calculate our construction work, or according to that we can calculate our mining orientation to save us from this sigma 1 direction, because it is a more stress direction, right? So that could be avoided for construction orient work. Okay, for watching, have a great day.